Okay, good morning everybody. Welcome to the mini Saturday morning session. We just have two speakers this morning. First up we have Suvrat Raju from ICTS Mumbai, and he's going to be telling us about the information paradox and black hole complementarity.
Okay. So thank you very much first of all to the organizers for inviting me here. This is my first time in South Africa. So I just got here yesterday evening and so far it's been very nice. Thanks again. So I'm going to give three lectures on the introduction to the information paradox and black hole complementarity. I was actually going to talk about something slightly different, and in fact, as I believe you already heard a series of lectures from Samir. So if you had to look at recent developments in the information paradox, you would roughly divide them into developments in two parts. So one of them has to do with evaporating black holes. Can you see at the back? I think a lot of the activity on evaporating black holes, which are black holes in flat space or small black holes in anti-de Sitter space, started in fact with Samir's work a few years ago, where he pointed out that if you refine the information paradox and you thought about the process of Hawking radiation carefully enough, then there was a problem here that you had to resolve, and one of the first symptoms of this problem was the so-called strong subadditivity paradox, which I think Samir already talked about. In fact, there's a second set of developments that in some sense have happened parallel to this that have to do with large black holes in AdS. So this version of the information paradox that deals with evaporating black holes is in a sense an extension of the earlier problems that people thought about, starting with Hawking's original work on black hole evaporation. More recently, there's been some work on also the information paradox in anti-de Sitter space. And this is the work that started with the work of AMPSS. In fact, there was a first paper which only had AMPS, which is slightly better known, which in fact goes into this column. But there's a second paper by AMPSS and some work by Marolf and Poczynski, and also some work that I did with my collaborator, Kyriakos Pavlodimos, which is focused largely on the information paradox in anti-de Sitter space. And this paradox is different. It doesn't have to do with evaporating black holes. It has to do with large black holes in anti-de Sitter space, which don't evaporate, which are thermodynamically stable, and has to do with understanding how the interior of such black holes can be represented in AdS CFT. So the question here is, how do you represent the interior in AdS CFT? Okay. So just to say that there's been a lot of recent activity in the information paradox, and roughly speaking, you would classify it into these two parts. I was in fact thinking that I'll talk about this side, but then this side requires a little more background and requires you to understand some aspects of this side. So in fact I changed the plan of my lectures a little bit, and I'll talk mostly about evaporating black holes. If you have time in the third lecture, I'll talk a little bit about the information paradox in anti-de Sitter space. But mostly I thought I'll talk about the evaporating black holes. And what I want to talk about primarily is a proposed resolution to the paradox here. So once again, this is somewhat complementary to what Samir said, and in fact the name of the resolution I want to propose is also black hole complementarity. And so the plan of my lectures is roughly to introduce you to the paradox for evaporating black holes and introduce you to the notion of black hole complementarity. Okay. So 1, 2, and in the third lecture, I actually want to give you an example of black hole complementarity in AdS. So the third lecture will be more of a research talk, and I'll talk about a very concrete example of black hole complementarity in anti-de Sitter space. Okay. So that's roughly the plan of my lectures. I have some lecture notes which I'll give to the organizers, and hopefully they can email it out to all of you. These lecture notes in a sense are excerpted from a larger course that I did on something similar, which also in fact talks about the right-hand side. And the lecture notes for this larger course I did are actually on my website. So those of you who want more details then are present in the lecture notes here. Should try to go to this URL. This is just my name. And one of the courses listed there is called Quantum Aspects of Black Holes. and that has a lot of details. And in fact, it's a superset of everything we'll talk about today. That being said, the lecture notes themselves are a superset of what we'll talk about in the lectures. So you should first try and look at the lecture notes we'll email out, and then if you want more details, look at this website. They're all handwritten lecture notes, but they're handwritten lecture notes that you might find useful. Okay, good. So are there any questions about this part, about the overview and where we are going? Okay, great. So let me just start off, what I'm going to start off today is try and tell you why we needed a refinement of the information paradox in the first place. And if you think about it, if you look at Wikipedia, you look at popular descriptions of the information paradox, popular descriptions of the information paradox go as follows. Now what they say is that we had a black hole. This is what's called a Penrose diagram for a black hole. We have a black hole. The black hole formed from collapse. So there's some star. And here's the horizon of the black hole. And this is an example of a black hole which formed from collapse. It's not an eternal black hole. At some point in the past, there was a star. The star collapsed into the black hole. The reason it doesn't look quite like it's collapsing everywhere is because this is a diagram where I've changed coordinates to make light rays go at 45 degrees. It's what's called a Penrose diagram. And then, Hawking found in a famous calculation that in this black hole, you get evaporation, and the black hole evaporates and emits black body radiation at a temperature which goes like 1 over the mass. Okay. And if you just take this very naively and you start pushing it a little bit more, you find that this evaporation of the black hole, which seems to come from the horizon, doesn't have any information about the star that made up the black hole. Okay. So there was some star that made up the black hole. The star could have been our sun, or it could have been some other star, or some star in a distant galaxy, or maybe it was just a collection of planets with the same mass. But the radiation that comes out of the black hole just depends on the total mass of what collapsed in, and on some other conserved charges, but on one parameter, which is the temperature, and not on anything else that went into making the star. Of course, the initial state of the star contains a lot of information. It contains a lot of details about what made up the star, what the configuration of various things was, contains a lot of microscopic details, but it looks like the radiation that comes out just depends on a few macroscopic parameters. Okay, so this is the most naive version of the information paradox, and it's the statement that, you could take star 1 and star 2, okay, and you form a black hole. And on both sides, you get out Hawking radiation. And the Hawking radiation that comes out of here is the same as the Hawking radiation that comes out of here. Okay. And of course, if that was correct, that would be in manifest contradiction with the fact that quantum mechanics fundamentally is reversible. Okay. If you look at the Schrodinger equation, you can evolve the Schrodinger equation given the wave function forward in time or backward in time. And if such a process really existed, then you could have two different stars which collapsed into a black hole, and they gave out the same Hawking radiation even though you started with two different initial states, and that would be in manifest contradiction with unitarity. Okay. So this is the most naive version of the information paradox. What I want to try and tell you today is why this statement by itself is not a paradox, and why this statement by itself is simply a statement of what's called thermalization of pure states, and why this, if you just had this paradox, it would be easy to resolve. So in doing this, in fact, I'll make some statements about statistical mechanics of pure states that will be useful and are useful to keep in mind. But at the least, the objective of my first lecture is to convince you that the fact that this process appears to happen, it doesn't really happen, is not very surprising in of itself. Okay. So are there any questions about this? Okay, and the final statement I want to make.
Sorry, these two, star 1 and star 2, are they of equal mass?
They are of equal mass in the example. Yes. Okay. So the point I want to make today is that is roughly that if you just made this statement, this is simply a reflection of thermalization of pure states. And the statement of thermalization of pure states is a statement that you can take pure states in a complicated enough system and you allow them to evolve, and very often, generically as a property of statistical mechanics, these states evolve into states that look to an excellent approximation. We'll try and make precise how accurately they look like thermal states, but up to exponential accuracy, you can take pure states in a generic thermodynamical system, and they can evolve into states that look thermal to an excellent approximation. For example, if you took the gas in this room and you broke the entanglement of the gas with everything outside, and so the gas was in a pure state by itself, the gas would still continue to look thermal to an excellent approximation for many, many observables, except for very fine-grained observables. Okay? So the first statement I want to make is that this process looks like it happens, but Hawking radiation is not really, the calculation of Hawking radiation is not really precise enough to distinguish this seeming process from the usual process of thermalization of pure states. Okay, so that's the point I want to make. And so to make that point, it's actually useful to try and understand first of all what it is that Hawking, what it is that went into Hawking's calculation when he derived this formula of T equals 8 pi m. In fact, the way Hawking derived the formula in his first paper was somewhat differently. The way Hawking derived the formula was by doing a process called ray tracing. I don't know if Samir spoke about that. Did you talk about the ray tracing? Okay. So the way Hawking derived his formula for this temperature equal to 1 by 8 pi m was as follows. Now he said, consider some body that's formed from collapse, and on this surface you have future null infinity, which is this region, and you have some past null infinity. And now you ask, what is the state of the quantum fields at future null infinity? And you can do that in a simple way, in fact, by just tracing light rays from future null infinity to past null infinity. And that's just a geometric ray optics problem. So in Hawking's initial paper, when he first derived this formula, what he did was he did a ray optics, ray tracing, of just rays going from past null infinity to future null infinity. And it turns out that all of the rays that reach future null infinity come just before this last ray. So this is what's called the last ray. And it turns out that all the rays that reach future null infinity at late times come from just before this last ray. So in fact, it's not a very hard geometric optics problem, but you can check that if you do this geometric optics problem, that gives you a transformation of coordinates from coordinates in the neighborhood of this last ray on past null infinity to coordinates at future null infinity. Okay, so if you have some affine parameterization of this part of space-time and some affine parameterization here, this ray tracing formula gives you a geometric way to go from coordinates here to coordinates here, and then that, using that formula, that geometric formula, he was able to show that if the observer at past null infinity thought that the observer was in the vacuum, then the observer at future null infinity would think that she was in a thermal state with this temperature. Okay. Now, in fact, this original ray tracing derivation is not precise enough to let you calculate corrections and also calculate how accurate this formula is. So sometime after Hawking's calculation, Candelas and others found a more precise way to derive this. And the first thing I want to describe is what is it that goes into this computation of the temperatures being 8 pi m. So I'll just try and state what the result that you find if you follow through this calculation of Candelas and others is. Okay. So if you have a black hole that's formed, are there any questions about this? I'm not. All I'm trying to do right now is try and make this precise and, as people say, problematize this statement and try and put the caveats to the statement and tell you what it is people mean when they say that the temperature of the final state is 1 by 8 pi.
You can actually show that the density matrix is some thermal density matrix with this temperature.
You can't show the density matrix is a thermal density matrix. That's a very hard calculation. I'll tell you what you can show. So the statement is, first if you look at a black hole, this black hole formed from collapse. But if you look at the geometry at late times, the geometry at late times looks very much like that of an eternal Schwarzschild black hole. And that's of course this. And actually we don't need to be in more than 4 dimensions, so we can just be in 4 dimensions from 4, let's say. Okay. Now, in this background, we can consider the propagation of some quantum field. In fact, the details of what this quantum field are is not important, but just for simplicity, we can consider some simple minimally coupled scalar field that obeys some wave equation. In fact, you can add a mass and you can add interactions to this field and that won't change this result. So this result that that these people found is rather robust. It doesn't depend on the mass of the field or any interactions, but you can think of some minimally coupled scalar field that propagates in this background. Then you expand this field in some complete set of modes. I'll tell you what these F's and G's are in a second. Okay. So we have this background, we have a quantum field, and then we take the quantum field, we solve this equation, we get a complete set of solutions. The complete set of solutions are things are called F and G. I'll tell you a little bit more about F and G in a moment. They're multiplied by some annihilation operators, which are these A's and B's. The A's and B's depend on the frequency of the wave and also on its angular momentum. That fixes the radial part of the wave equation. And then there's of course the Hermitian conjugate that goes in. So I'm not doing anything very complicated here. This is the usual expansion you see in quantum field theory. Okay. Now it's convenient in all of these black hole discussions, in fact, to go into what are called tortoise coordinates. Tortoise coordinates are those coordinates that say that where dr by 1 minus twice m by r is 1 minus twice okay. So it's just a change of variables from this r to some other coordinate r star that has the form that this part of the metric starts looking like the time part. And that's just useful because then the dr star part becomes conformally flat. Okay. So it's very useful in all of these discussions to use this so-called tortoise coordinate. If you don't like it, you don't have to use it. Everything I'm saying, is just a change of variables from this r. You can just solve this equation, you'll get some formula for r star. But in terms of these tortoise coordinates, these functions f and g have the following form.
A and B as well? Like, why are there two annihilation operators?
Yeah, one second, I'll tell you what they're doing. Okay. So the reason there are two annihilation and creation operators is because when you think of waves propagating in this basis that I've written things in, so notice that the way I've written things in is in terms of spherical waves. Okay. So there's a time part, there's an e to the minus I omega t. Both of these have an e to the minus I omega t. Then there's some behavior in the sphere, which goes into this spherical harmonic. Okay. Then there's a question of how these spherical waves behave at the horizon and behave out at infinity. So these waves, this f omega L, are waves which are outgoing at infinity. Okay. That you can see from the behavior as r goes to infinity of these waves. They have some behavior that goes out at infinity, and these a omega L's are terms that you can get by solving the wave equation. So the boundary conditions that you get for finding this solution are actually that you fix the behavior at the horizon. Okay. So you fix the ratio of this part of the horizon to be 1, and then everything else, the A's and the B's, okay, just come from solving the wave equation after that. Okay. The same way, these waves are waves which are ingoing at the horizon. So remember, the complete set of bases is not given by waves which are outgoing at infinity and ingoing at infinity. Okay. That's because if you have a wave that's ingoing at infinity, some of it bounces back because of the potential and goes out. So the independent set of solutions is not given by waves that are outgoing at infinity and ingoing at infinity, or outgoing at the horizon and ingoing at the horizon, but rather the correct basis to choose is waves that are outgoing at infinity and ingoing at the horizon. Okay? So that those are the waves that are independent, and these f's and g's are the wave functions that multiply those two waves. Okay, so that's why you have two creation and annihilation operators.
If there was just some arbitrary other potential but not the horizon, then the usual would have been okay?
What do you mean if there's some arbitrary other potential?
Meaning, now you are specifying in terms of some boundary condition horizon.
Yes.
So there is some other gravitational potential, not the horizon.
So if you, for example, it depends on what kind of potential you have. For example, if you're an anti-de Sitter space, then indeed there's only one wave because the boundary conditions at infinity are force that lead you to have standing waves. So if you're in this kind of a situation where you have standing waves, then there's only one kind of a wave, which is what happens in anti-de Sitter space. In this kind of a setup, you don't have standing waves. You have waves which can go in and waves which can come out. So there's flux which can go in and flux which can go out. Okay, so you have two different kinds of creation and annihilation operators and two different kinds of waves. And in fact, from here, the result that Candelas and others found is as follows. Once again, I'll refer you to the notes if you want to see the details of the result. I'll just quote the result here. The statement is that if there is, let's say the black hole is in some state U, okay, then the statement that there is no incoming radiation from infinity, okay, tells us that this part, the B parts, annihilated. And that's because the B parts also have some ingoing part at infinity. Okay? And therefore the statement that there is no ingoing radiation from infinity, you're not throwing in any radiation from infinity, tells you that this state satisfies this. Secondly, if you demand that the horizon is regular, just demanding that the horizon is regular tells you that you can compute two-point correlation functions. In fact, the precise calculation that Candelas did was that of the stress tensor at the horizon. So it tells you the two-point correlation functions of this A are the following. Okay, so this is the usual thermal two-point function that you get as a delta function. And the statement is that if you look at the two-point function of these A's and demand that the horizon is regular, then you can find that this two-point function has to have this form. This state U is what's called sometimes the Unruh vacuum. It's almost defined as a vacuum in which the future horizon is regular. And what Candelas and others found is that to ensure that the future horizon is regular, you have to ensure that this two-point function has this form. Now you can do a little bit more. You can try and include effects of back reaction. You can try and compute higher point functions. But the fundamental calculation has to do with the behavior of the two-point function, and that's what tells you that's what tells you the state, not quite the state, but some part of the state of the fields outside the horizon. In fact, the same calculation also tells you about entanglement across the horizon, which I think Samir spoke about. So you can use exactly the same calculation. You can expand waves behind the horizon, and the same calculation will tell you about the existence of a two-point function of waves in front of the horizon and waves behind the horizon, but I won't talk about that in this lecture. So in this lecture, what I'm focused on is the fact that demanding that the horizon is regular and just solving the wave equation leads you to a calculation of a two-point function, and this in a sense is the precise version of Hawking's calculation.
What does regular mean? What do you impose to say regular?
Well, what you impose more precisely is that the short distance behavior of the two-point function here is the same as that in flat space. So the thing that you impose is that if you look at phi of x prime, you look at this correlation function, and you look at limit as x tends to x prime, then this correlation function goes like 1 by x minus x prime squared. So this is actually a very mild statement. This is the statement that there's no singularity at the horizon. So you impose this everywhere. it's a statement that holds in our world. It holds for any quantum field theory that's governed by an ultraviolet free fixed point, and what you demand is this. Okay? So if you just demand this and you do this computation, you'll find that unless this 2-point function is this result won't be right. Okay. So this is the precise, this is really what you can say by demanding that the horizon is regular. Now, as I said, you can do more. You can try and work harder, and you can try and include corrections to this computation. But what I want to show you is that this statement by itself and the other statements that you can get by trying to correct Hawking's calculation by including corrections in perturbation theory by themselves are not enough to lead to a paradox. Okay? So the first point I wanted to make was this point about what it is you mean when you say that the temperature of the black hole is 1/8πm. What you really mean is that if you quantize the field in terms of modes that are outgoing at infinity and ingoing at the horizon, then you start with some state and you don't insert any material that goes in from infinity, and even then you end up with this situation where there's a 2-point function, a finite 2-point function, and it looks thermal, and this beta is 1/t, where t was what I had.
But since you have the scalar field coupled to gravity and which is autodynamical,
Yes.
saying that I go to the UV, doesn't it, don't you have to take into account the fact that your gravity when you take it to higher and higher energies?
Good. So this is a condition that you impose. So you shouldn't say limit as x goes to x prime. You should say you take x goes to x prime, so x minus x prime is smaller than all other scales in the theory, but x minus x prime is also much larger in the Planck length. Okay, so any questions about this part? Okay, good. So now the next statement I want to make is a statistical mechanics statement. It's a statement that if someone tells you that I have a system and I computed a 2-point function in the system. The 2-point function I computed looks thermal. Okay. Can all of you read this, by the way? I'll try and erase better, but you're not getting. Okay. So someone comes to you and says, I have a system. I computed a 2-point function in the system. The system looks thermal. Therefore I feel that the state is in a thermal state. And that statement is a misleading statement. Okay? And that statement is a misleading statement, and that's because of the next statement I want to make, which is that pure states So if someone just computed for you, this 2-point function, that by itself doesn't tell you that the state U is mixed. And that's because of this statement, which is that even though we tend to think of pure states as somehow eigenstates of the Hamiltonian and somehow different from thermal states, that's in fact not true. And pure states, for almost all practical purposes, in fact almost all pure states, mimic thermal states to very great accuracy. Okay? So that's the second statement I want to make, and I'll try and make this statement precise now. Okay. So the way you prove the statement, and I'm going to try and make precise also what it means by very high accuracy. Okay. So to understand this claim, what you should do is you should think of some complicated system which has a lot of degrees of freedom. So if you take some thermodynamic system, then in general the thermodynamic system has a Hilbert space, and we'll write down a basis for that Hilbert space, and that basis has some there's some eigenbasis. You can choose whatever favorite operator you like. And the basis has a number of vectors, but the number of such vectors is e to the s. Okay? That's because when we say that the entropy of some system is s, what we really mean is that the dimension of the corresponding Hilbert space is e to the s. Okay, is this something all of you are? So when we talk about the entropy of the system, what we really mean is that the dimension of the Hilbert space, of the quantum Hilbert space that corresponds to that system, is exponentially large in the entropy, and it goes like e to the s. However, in fact, the number of states in the system is infinite. The number of states in the system is not finite, and that's because a typical state in the system is a linear combination of these states, and it's this. Right? where this I goes from 1 to e to the power s. Okay. So the actual number of states in the system is given not by giving me one of these numbers, but by giving me e to the power s numbers, and all of these e to the power s numbers are continuous. Of course, there's a constraint which comes from normalizability, which is the sum of ai squared has to be 1. So the state has to be normalizable, has to be correctly normalized. But apart from that, the set of number of states you have is actually a manifold. Okay? In fact, this is okay. So it's a manifold which it's not quite a sphere, but this manifold is Cp e to the s minus 1. Okay? So you have to give me e to the s complex numbers, okay? But then I can mod out by any one complex number, and then I have e to the s minus 1 degrees of freedom. Okay? So just to point out, one thing you should keep in mind is that when I give you a complicated thermodynamic system, even though the dimension of the corresponding Hilbert space is finite, it's large but finite, the number of states in the system are infinite, and they live in a continuous manifold, which is this manifold, okay, which is parameterized by these numbers, ai. Okay, so the question that you want to ask about how pure states behave and how observables behave in a typical state of the system is a question that can be answered by trying to average over this manifold. So the question that one wants to ask to understand how pure states behave. In fact, let me add one more word here. Almost all pure states. Almost all and very high. So when I talk about almost all pure states, what I mean is that for most of the volume in this manifold, in this continuous manifold, the state that I have, which is a linear combination of these eigenstates, will look exactly like a thermal state. Okay, but now how do you determine what most of the volume in this manifold is? What you do is you try and write down some measure that treats all of these coefficients ai democratically. Okay? So what you try and do is you want to ask for
could you have also imposed the fact that higher point functions of phi should also behave in a conformal way?
Yes, you could impose this for higher point functions, but even that won't be enough. Even that won't be enough. I'll come back to that at the end. Okay, so so let's say you have some observable A. This is not the earlier A that I wrote. It's some observable A. Well, for example, A could be this product of creation and annihilation operators, or A could be a 4-point function, or A could be some 10-point function. Okay? So A is some observable, and when I write this double bracket, what I mean is that I do an average over this Hilbert space of this. But this measure mu is some measure that basically averages democratically over these coefficients ai. So it's not very hard to write down such a measure. The way you write down such a measure is basically you just write down d of ai and put a delta function that tells you that 1 minus sum of ai square has to be 0. So it's not very hard to write down this kind of a measure. This measure is what's called the Haar measure on the Hilbert space. Okay? Once again, I'm not going to give you details of the proof that go into this, but this is again not hard to do, and it exists in these notes that I referred to. But I just want to tell you that when one talks about what the value of an observable in a typical state is, when we use the word typical state, what we mean is that you look at the expectation value of this observable in a pure state, and then you average over all pure states. Okay? By averaging over all pure states, it's not a discrete sum, but rather a continuous integral that you have to do. It's a continuous integral that tells you have to average over all of these coefficients ai, okay, after imposing this delta function. And that is what one means by the typical expectation value of an observable A in a pure state. Yes?
Presumably, if you have a goodic system, this is just a time integral.
Maybe this is just a time integral, yeah. But I'm not going to make that assumption. In fact, the statement I'm going to say right now is very, it's very general, and it doesn't even involve this assumption that you just mentioned. Okay. So the first statement is that's very easy to prove, is that this expectation value of A is in fact just trace of A divided by e to the s. No, this was almost guaranteed to be the case, because you see that this expectation value of A, you're averaging over all states, right? So what would you get? If you just try to compute the expectation value of A, whatever matrix element that you have, the answer that you get is something that can't really depend on the basis that you chose to set up the Hilbert space, and therefore basically the only answer that you get can't involve any matrix elements of A, and it turns out that the answer that you get for the expectation value of A in a typical state is just the trace of A divided by e to the s. Okay? But what is the trace of A divided by e to the s? This object is the expectation value of A in the microcanonical ensemble. So do you understand why this statement is the case? You see, in this setup, I've taken 1 to e to the power s states. Okay? For simplicity, I was considering a Hilbert space where these were all the states that you like. But if you wanted to think of a setup where you had a gradation of energy states by the Hamiltonian, then you would think of these states as living within some energy band that you're interested in. And then the trace of an operator over all of those states is what you mean by the trace, expectation value of an operator in the microcanonical ensemble. This is not the expectation value of an operator in the canonical ensemble, which will have an e to the minus beta h here. Okay? And of course, no such object can possibly appear because we never put in the Hamiltonian in our discussion. But this trace of A is the expectation value of an object in the microcanonical ensemble, and that's a mixed state. Okay? The microcanonical ensemble is almost it's a prototypical mixed state. So this result tells you that if you take a typical state, and by that I mean you look at all possible pure states, and then you average over all possible pure states using the Haar measure in the Hilbert space, then the answer that you get looks exactly like the answer you get in a mixed state. Okay? And the reason this is the microcanonical ensemble is because the microcanonical ensemble is a unit density matrix where each eigenvalue is 1 by e to the s. Okay. Okay. Now you might have said, okay, maybe.
Is it a computation or just an expectation?
No, it's some sort of a computation. It's very easy to prove. It's not an expectation. Sorry, I'm quoting some results here, but this is a theorem. Okay, it's a theorem that was. I don't even know if it was. It certainly was proved by Lloyd in 1989, I think, but it's a very simple theorem to prove. It's not an expectation. Okay, so this is a theorem. I don't want to emphasize too much on the theorem part. It's a 5-minute calculation to do this, and I'm happy to show you. And it's in those lecture notes that I mentioned. Okay. So I'll put it in these lecture notes also. So because it's only a 1-hour lecture, I'm going to try and quote some results, and I won't go through all the derivations, but I'll put the derivations in so you can look at all of them. Okay. The second statement is you might have said, maybe because you averaged over all states, you got the expectation value, but maybe individual pure states are different. Okay? So maybe you see this could happen in many ways. It could be that in all pure states, this value was always 1 or minus 1. And because there are so many pure states, you somehow average out to 0, which is what you get in a mixed state. But if that was the case, then you would still be able to distinguish between pure states and mixed states by looking at this operator, because the moment you got a non-zero value, you would know you're in a pure state. Okay? So just looking at the average and saying that the average expectation value of some operator is the same as the expectation value in a mixed state is not enough, may not be strong enough. And you might still believe that somehow pure states tend to differ widely from this average. Okay? So it might be that individual pure states differ from this average. But in fact, this is also not true. And the second statement is, which is also a theorem, and involves a slightly harder calculation, but once again not very hard. Is this. So now look at the expectation value of A in some typical pure state, and look at how much it deviates from this mean expectation value. Okay? And take that deviation and integrate that deviation over the full Hilbert space. Okay? And it turns out that this is given by the right hand side of the following. In fact, the answer I'm writing down is an exact answer. It doesn't require any assumption that S is large. It's the exact answer. So the statement is now, that you look at the deviation of expectation values of A from their value, from the value you get in the mixed state, and you ask, how much does the expectation value of A differ from, the mean expectation value in pure states. You take that, you square it, so you always have a positive number, and you integrate this positive number over the full volume of the Hilbert space. Okay. Then the statement is that it's given, the right hand side is given by this. But what appears in the bracket actually is something rather simple. What appears in the bracket is roughly the standard deviation of the operator A. You see, we have trace of A by e to the s, which is some finite number because it's the expectation value you have in the microcanonical ensemble. And then you have trace of A squared by e to the s, which is, it's basically the expectation value in the microcanonical ensemble of the operator A squared. So this bracket you can recognize as the standard deviation of A. It's roughly, what trace of A squared is, the expectation value of A squared minus the expectation value of A the whole squared. Okay. So this is some finite number, and what you have here outside is some big factor of e to the s. And therefore, if you have a big Hilbert space, so far this result has been exact, if you have a big Hilbert space, it tells you that not only is the expectation value of an operator in a typical pure state that of the same operator in the microcanonical ensemble, but in fact the deviations of the expectation value of the operator are suppressed by a factor which is exponentially large in the entropy. So these two statements together make precise what we just said. They tell you that the typical pure states resemble the microcanonical ensemble to exponential accuracy. Okay, where exponential means e to the s. Okay. So this is in fact it's a very simple statement. And as I said, these results are not hard to prove. It's a simple computation that involves writing down the explicit form of this measure and just expanding this out and doing the various integrals that you get. There's some spherical integrals you need to do. But the result is the important result. And it's a statement that if you look at typical pure states that resemble the microcanonical ensemble, it's not that they resemble the microcanonical ensemble up to factors of 1 by e to the s. Okay? So remember, for example, when you prove the usual equivalence of ensembles between the microcanonical and the canonical ensemble, that equivalence is something which is true up to 1 by s factors. It's a power law resemblance. In fact, typical pure states resemble the microcanonical ensemble up to exponential accuracy. And that's what you get out of that result and this result. Okay. So pure states are, typical pure states are not distinct from the microcanonical ensemble. Some very special pure states might look distinct from thermal states, but if you give me some democratically picked pure state just by taking the Hilbert space and picking some point in the Hilbert space, then that space will look exactly like a mixed state. So you can't use expectation values of simple operators, provided they have a finite standard deviation, to distinguish between pure states and mixed states. Okay. So that's an important result that I wanted to emphasize. And then I'll stop here for questions to see if there are some questions.
This expression, this theorem was also generally true for small s as well? Or?
No, this theorem is again an exact theorem. So this is an exact statement, this is an exact statement. Now if e to the s is 1, I shouldn't even be using e to the s, then you may say they don't resemble things because the deviation is order 1. But this statement now is a statement where I use large s, when I said exponential accuracy. So exponential accuracy of course makes sense only if the exponent is large. But this is an exact result. That's why I put a +1 here. Okay. So I put a +1 here to indicate that this is an exact result. It's not I haven't made any approximation proving I did this or this.
Can you use this thing to also show that arbitrary correlation functions would also behave in
correct. Correlation functions are a special case of this. You see, this correlation function is a special case of this, which has A is equal to A omega dagger A omega. correlation function is a special case of that, with A being this. So correlation functions are expectation values of operators.
But I mean, arbitrary correlation functions with a lot of things inside it.
How does it matter? They're all operators. This operator A is a general. I didn't say
So you
anything
can
about
have
this operator
like,
A.
okay.
Yeah, I didn't say it was a local operator. You know, what appears here is the standard deviation of A. You need to keep that finite, but other than that, you know, you could take a 10-point correlation function or 20-point correlation function. Now, if you started taking A to be an S-point correlation function, then you might run into trouble because, you know, the standard deviation of A might diverge. But, you know, provided you have a finite point correlation function, you don't run into any trouble here.
For pure states that don't mimic thermal states, you have in mind things like many-body localized states?
Yes, there are states which don't mimic the thermal state, but those states are exponentially unlikely in the Hilbert space. So there are two things that come out of this. There are two things that could happen. One is your deviation of this from the thermal state could be large, but you know it's large, but it's killed by the volume factor. So the volume that it occupies is exponentially small. The other is that the deviation is small, and that occupies a large volume. So there are states which don't mimic the thermal states, but those states are exponentially unlikely. So in fact, many of the pure states that we like to talk about are exponentially unlikely states, which is not surprising. Now, we like to talk about very special states, but those are not states which are picked in the full Hilbert space. They're states that we pick because we like to study some property of those states. But in the full Hilbert space, they're exponentially unlikely. Okay. Any other questions about this? Okay. So you see that what these results tell you is that you know, the statement that I just made right now, which was that the 2-point function of these A omega dagger E omegas looks thermal, is not enough to tell you that this state U is a mixed state. What it's enough to tell you is that U looks a little bit like a mixed state in that you computed the 2-point function, and you could do more. You could try and compute a 4-point or a 10-point correlation function, and those calculations become harder and harder and harder. But you know, every time, even if every time you got a thermal answer, I would still say, oh, that's not so surprising, because I expect that unless you go, you know, you compute things up to exponential accuracy, where where S is the entropy of the black hole, I don't even expect you to start seeing differences from, you know, the mixed state answer. So the fact that you can compute these 2-point functions by itself doesn't tell you that the final state is mixed. Now, as I said, that's not at all to say there's no information paradox, but it just means we have to be more clever in phrasing the information paradox. And so now what I want to do next is try and, you know, tell you how you can refine the information paradox to get a genuine paradox. But the first point, and the point I'd really like all of you to take away from here, is that, you know, whenever somebody says that as Wikipedia does, you know, that the information paradox is the statement that you know, the Hawking radiation is thermal, and that looks like it's in contradiction with unitarity because the initial state had information. That's just false. Okay, that's not the information paradox. Okay. Okay. So now so what is it? What is the information paradox? How do we try and refine things to try and come to a paradox? So that's what I want to talk about next. About 10 minutes left. Or
15%.
Okay, good. So the first step to doing this refinement is to use a result of Page. And that result is as follows. The first step to refining the information paradox is to try and understand how fast information has to come out. So how fast is it that information has to come out? Of course, unitarity of quantum mechanics tells you that if you started with a pure state in the beginning, then you should end up with a pure state in the end. But as we can see, that's something that's very difficult to test, because you would have to either compute the exact state, or equivalently you would have to compute arbitrarily high point correlation functions. And that's something which is very hard to check. Of course, if you had an exact description of the system, you could check it, but we don't have an exact description of quantum gravity, or at least we don't have an exact computable description of quantum gravity, okay, where we can compute in the bulk exactly how the state evolves. So in fact, the way to refine the information paradox is to be more clever, and the first step in doing that is to have a result is to derive what's called the Page curve. And the Page curve is a statement about how fast information exits the black hole. So the main technical tool in the page curve is what's called the entanglement entropy. Okay, so for now, don't think so much of the Penrose diagram, but think of the following picture. So here we have a black hole, and we have some region outside, and I'll call that region outside A. Okay, so we have some region outside the black hole. That region outside is A, and the question we want to ask is how fast does information from the black hole enter into the region A. Okay? So one way to do that is to think of the region A and is to trace out everything that's not the region A. So let's think of the outside of the black hole. So we draw some imaginary line outside the black hole. Everything outside that is the region A. Everything inside that I'll specify maybe in the next lecture, but for now is not important to us. Okay? We want to ask how fast does information from the black hole enter this region in the exterior. So how do we quantify that? One way to quantify that is to look at how mixed A is. And one way to determine how mixed A is to look at the density matrix of A and to look at the entanglement entropy of A, which is this. Okay. I don't know how many of you are familiar with entanglement entropy. But roughly speaking, entanglement entropy, it does many things, but one of the things entanglement entropy can do is it can measure for you how mixed a state is. The entanglement entropy is not given by the expectation value of any observable. So it's not something that fits into the theorem that we proved last time. The entanglement entropy is actually a non-linear observable. It's not given by the expectation value of any linear observable. But the entanglement entropy can determine for you how mixed the state is. So it's one of those observables that can differentiate between mixed and pure states. In particular, for pure states, entanglement entropy is 0. Okay. And the entanglement entropy is log of the dimension for the microcanonical state. So it ranges between these two values for other states that may be less mixed or than the microcanonical state. So there are some extreme values you have for the entanglement entropy, and it takes on some set of values in it. And it's defined in this way. And for those of you who haven't seen it, I'm happy to talk after class and try and explain to you what the entanglement entropy is in class. Okay. So now what we want to look at is we want to look at the entanglement entropy of A. And we want to use the entanglement entropy of A to determine if the radiation that's coming out of the black hole is mixed or the radiation is pure. Okay? So naively, you might have thought that the way to measure this is to first say that A is empty. Okay? There's nothing in A in the beginning when the black hole has not evaporated at all. And in the end, when all the Hawking radiation has come out into A, then A is pure. So you might have thought that one test of unitarity was somehow that this entanglement entropy of A was 0 in the beginning and 0 at the end. In fact, there are some problems there are two complications in trying to make this precise. And one of them is that if you look at this S of A, okay, S of A is not equal to 0 even in the vacuum. Okay, so even if you didn't have a black hole, but you just had the vacuum, and you try to look at the same region of space, you would still find non-zero entanglement entropy. And that's because whenever you have a quantum field theory, that quantum field theory has a lot of entanglement between one region of space-time and another region of space-time. And this is in fact a property that we will use in the third lecture. But different regions of space-time are entangled. And in fact, the reason our the geometry that we see looks smooth is because different parts of this room are actually entangled with each other, even in the vacuum. So in any local quantum field theory, even the vacuum has a lot of entanglement between different parts of space-time. So when we want to ask the question of how fast information exits the black hole, and we want to measure that using the entanglement entropy, the first thing we would like to do is we would like to, look at the entanglement entropy of A in the state, but subtract off the entanglement entropy in the vacuum. So, roughly speaking, what we want to do is we want to look at the difference of the entanglement entropy. We want to look at the entanglement entropy of the matter that exists in A, and so we want to subtract off the entanglement entropy of the vacuum. So that's the first thing to keep in mind. By the way, I should say, in what I'm saying right now, none of this has, as far as I know, ever been made very precise, and so these are things which are worth thinking about more, even though I'm giving you some answers here. So the point I'm making right now is that often people try to measure the purity of the state outside by looking at this entanglement entropy. But if you think about it carefully, you realize there are two complications. One of them is that you have to subtract off the entanglement of the vacuum. The second problem is that no one has succeeded in making the definition of entanglement entropy precise in the theory of gravity. Okay? And that's because the entanglement entropy is a statement about, it's a statement that involves always a notion of locality. Entanglement entropy is something that requires you to be able to factorize the Hilbert space into the degrees of freedom in one part and the degrees of freedom in another part. Okay? So just to say, the reason that's the case is because we want to write down some density matrix that corresponds to this region A, and to do that we have to trace out everything that doesn't belong to this region A. But to be able to trace out everything that doesn't belong to the region A, you have to be able to have a notion of what is local, what is it that you should include in the degrees of freedom in A, and what is it that you should not include in the degrees of freedom in A. So whenever you talk about the entanglement entropy of a region, you have to have simultaneously a notion of locality. What is included in the region and what is not included in the region. Now, in fact, in the theory of gravity, this is something tricky. Even in gauge theories, this is something that's tricky, but it's something that we seem to understand how to do at least somewhat well. But in theories of gravity, this is very tricky because we don't have a notion of local gauge invariant degrees of freedom. And the reason for that is that if I try to put some mass here, this mass always has a Gauss law tail that goes out all the way to infinity. I can detect the presence of some mass m just by seeing what happens at infinity. And there is no way to shield the presence of the mass m from infinity. In gauge theories, at least you could put a charge q and you could put some other charge minus q around it, and so you would be able to shield the presence of that charge from infinity. And so there are some local gauge invariant operators. In gravity, there are no local gauge invariant operators at all. Okay? So now we do believe, nevertheless, that there should be a good definition of entanglement. There should be some approximate definition of entanglement entropy, but no one has ever succeeded in coming up with a precise definition of entanglement entropy in theories that include gravity. Okay? So whenever I talk about the entanglement entropy of the region A, you should keep this caveat in mind. So at least for the first caveat, we have some answer, which is that you subtract off the entanglement entropy of the vacuum. For the second caveat, we don't really have a good enough answer, except for believing that there should be some way to define the entanglement entropy, which takes into account the entanglement of the matter, but somehow doesn't get stuck on this complication, which is the fact that you don't have local degrees of freedom in gravity. So there should be some parametric limit in which you should be able to switch off these degrees of freedom, but as far as I know, that's never been made precise. Okay.
A related comment, I mean, tell me if you agree, is that since in gravity the space-time manifold itself is made by gravitons, even talking about where the region A is ceases to make complete sense.
That's
Before
part
even talking about what is inside or outside.
Yes, that's part of the problem. That we also don't know how precisely to define the boundary of this region A. That's because what do you mean by the region A? So one way to frame it is if you had some fixed boundary very far away, you could say, I jump in with some velocity, and then the region A is after 10 seconds of proper time have passed. But these are all very classical notions. So while classically you can make sense of these, if the space-time is fluctuating, it's very hard to make sense of these things. So it's and that's actually part of the problem. It's a closely related problem to the fact that we don't have local gauge invariant degrees of freedom. Okay. And nevertheless, if you ignore these complications, then the result of Page was in fact that if you look at a typical state, a typical pure state, the same typical state, and the techniques that Page used were precisely these techniques of trying to average over the full Hilbert space, then you find the following. then what Page found was the following. As if in whatever state of the black hole we are in, subtract off the vacuum. What Page found was the following. So in the beginning, you see this region A is the vacuum for all practical purposes. So when the black hole starts evaporating, the region A is empty. So it doesn't have anything in it. And therefore this entanglement entropy starts at 0. Okay. Then, various Hawking radiation starts to come in, and Page argued that this behavior increases monotonically till some point which is called the Page time. And then it must decrease monotonically. Goes back to 0. Okay. So this curve is called the Page curve. So what Page argued was that the information paradox is not just a statement about the fact that in the end the entanglement entropy should be 0. You see, so far what we were talking about was the statement that in the end the Hawking radiation should be pure. That's this part of the Page curve. It's a statement that finally all matter should come out. All the information should come out, and therefore the state should be pure in the end. But what Page pointed out was that if you think a little more about pure states and use genericity, it's not just that information must come out here, but information must start coming out when half the black hole has evaporated. So this point is roughly the point where the Bekenstein-Hawking entropy of the black hole also meets this entanglement entropy. So this is the point when the entropy of the black hole has reduced, when the area of the black hole is reduced by a factor of 2, this turnaround point. Okay. And this point is a time that occurs in time of order n cubed, you can check. It's where m was the mass of the black hole. So in a time of order m cubed, when the area of the black hole is reduced by a factor of half, Page pointed out that the entropy of the black hole must in fact start decreasing and must go down to 0. Okay. Let me just tell you what the result that Page proved was, because when I saw this result for a long time I was very mystified. So in fact Page used exactly these techniques of averaging over pure states which are used to prove the past two results. And what he proved was the following. Okay, and then he interpreted it in this way. And he said, consider an nm dimensional space. But without any loss of generality, we'll assume m is smaller than n. Okay, so we have a Hilbert space which is mn dimensional, and so this Hilbert space is a product of hm. You decompose it into hm and hn. Okay. And we assume without any loss of generality, m is smaller than n. Whatever the smaller factor is, we call that n. Okay. Then he proved that if you look at a generic pure state in this full Hilbert space, let's take psi to be. Then look at the density matrix of m and trace out all the degrees of freedom in n. Then he found that Fm was log m minus m squared. Okay. So this is a statement that if you take a generic state in a big pure state, okay, which is a product of two factors, it has m into n, then the entropy of that, in that generic state of one of the sub-factors, the entanglement entropy, is log of the dimension of the smaller factor. Okay. So the way you get this curve, and the reason it looks like a straight line going up and a straight line going down, is first of all m by 2n. Oh, sorry. Okay. Is because these corrections are much smaller than the log term. Okay. That's because these m's, remember, are e to the s. So in these big thermodynamical systems, the dimensions of the Hilbert space involved are always e to the times the entropy of the system. So this is some correction which is order 1, whereas this is some term which is order s. Okay? So these are power law suppressed corrections. They're not exponentially suppressed, but they are power law suppressed. And what they tell you is that here, when you look at this system, you imagine that you have a factorization of the Hilbert space into the Hilbert space outside, into H inside, times HA. Okay? So you imagine that the Hilbert space factorizes into a Hilbert space of A into the Hilbert space inside this region. Now you ask, which is the space which has more degrees of freedom? In the beginning, the inside has all the information, so that's the part which has more degrees of freedom. It continues to have more degrees of freedom as matter and energy leak into A, and therefore this entanglement entropy goes up monotonically. Eventually, the larger, which one is larger flips, and that happens at this point. That happens when A has more of energy or more information than the other part, and then you use the same result, but now the size of the smaller part is becoming smaller and smaller. That's because more and more information is going into A, and so that's why you use this. You use this result, but you use the fact that for the first half of evaporation, it's the inside which is the larger factor, and for the second half of evaporation, it's the inside which is the smaller factor, and that's what gives you this curve. And once again, to prove this result is not hard. It again involves doing the same average over Hilbert space. Okay, so just you use this hard measure and you do this average. It's again doing some computations, and you can prove this result. So this is the first step towards refining the paradox, which we'll do next time, and towards trying to argue, why there is still a problem that we'd like to understand and understand better and resolve. And the first step to doing that is to look at how fast the information comes out. Okay. So I'll stop here. Let me just recap very quickly what I did. You see, the first statement, which is the popular statement of the information paradox, is that Hawking radiation looks like it depends only on the temperature, and that looks like it's in contradiction with unitarity. Okay? And what I'd like all of you to recognize is that itself is not in contradiction with unitarity, because many pure states look exponentially close to the mixed state. So many pure states don't look like they have any features. Many pure states look exponentially featureless. And that's a theorem in statistical mechanics, which you can prove just by looking at pure states without almost any assumptions. Okay, so sometimes people make assumptions in proving theorems in statistical mechanics, in thermalization, the so-called eigenstate thermalization hypothesis, the ergodic hypothesis that you mentioned, but you don't need any assumptions to prove this. So the fact that pure states are featureless is a very general result in statistical mechanics. So we need to work harder to understand the information paradox. And the first step in working harder is to understand and appreciate this page curve. This page curve is a statement of how pure the outside is and how fast the information has to come out. And the page curve is based on an argument of genericity. It says that for a generic state, if you try to divide a generic state, and you had some evaporation of a black hole in a generic state of the theory, then in this generic state, if you measure the purity of the radiation outside in terms of its entanglement entropy, that entanglement entropy would be a curve that looks like this. Okay? And now we can think about this curve a little more, as we will do tomorrow or day after tomorrow, and try and understand why there's still a paradox. Okay, so I'll stop here.
Thank you very much. Are there any further questions? Okay, if not, well, I guess you'll be around for the next couple of days anyway, and we return on Monday for more. So I suggest we come back at 11:05 after coffee, but let's thank Suvrat again.